Alright, let's continue exploring reachability graphs. And in this video, I'm going to show you how they can point out costly dead ends, that is, dead ends that are paths that are dead ends or very time consuming paths before you get into them. To do that, I'm going to set the stage, however. So, you're a tester working with an international video game development company, and you're testing the latest version of Space Treasure Hunter, the multiplayer edition. Now you've been testing this game for a while. This is the splash screen, and you've been testing this for a while. It actually appears very robust, pretty good, pretty clean. And today you began a testing session and saw the following text in the usual dialog box. Let me see where the screenshot is. Alright, so you see this is a usual screenshot of the dialog box you get every time you initiate the game. You see a text, press start to play, but now you see a fatal message. Okay, now you know that another teammate, Jenny, mentioned that she was using the same system to run security tests the night before. So you take a screenshot of this and you press start to play, and the game seems okay. Everything looks normal. The game loads the level you're at, the save level, with the correct number of NPCs, the non-player characters. You also check the stats of the game and they look correct. The stats like frame per second, etc. They look fine. So that is very strange. So you decide to quit the game and restart it. But this time, a different text appears. An error. Now, you notice that you can't load any level. The game appears to be stuck at that dialog box. There's a lot of work that needs to be done in terms of testing, support, serviceability, diagnostics, log collection, etc. Because this is just not enough. This is unacceptable. Error and then call support is unacceptable especially for a video game. But now you're wondering what happened. Did Jenny leave the system in an unstable state? Should she be called in right now to explain what she did? Should you revert to an old snapshot with a known state? I mean, could this be an instance of the infamous Oracle problem? There's several things you can check. I mean, you can check out what's going on with the password. I mean, you could actually see if encrypting the password resolves the issue. But I would suggest first relax. Alright, relax. Testers typically go through scenarios like this one almost every day. Since we don't have an infinite amount of time, we need to optimize the effort we spend investigating the system under test, especially states like these, bizarre states like these. And that means not wasting time on paths that might lead to dead ends or are simply irrelevant. Now, I'm willing to bet with 95% confidence that your mind is already telling you that the password message, something with the password, is related to the error. Okay, as we said before and we said again. So I can tell you, even in this hypothetical example, it's not. But how can you tell? Well, there's a phenomenon that we testers need to watch out for. That phenomenon is called mental anchoring. And anchoring is one of the many biases that cause us to make incorrect decisions during testing. Mental anchoring is a cognitive bias. And in general, biases make you assume things which might not be true. In particular, anchoring is when you first see something and then the next thing you see, you already have you're already preconditioned to weigh in the previous. It's almost like probability. The prior probability affects the subsequent probability. Okay, so biases mean that you waste your time, your precious time. But even seasoned testers are prey to biases such as anchoring. Now I'm going to show you in this video how to use reachability graphs, so you can actually let the system under test. So with this technique, I'm going to show you the system under test will actually tell you what is relevant and what you can ignore. Alright, in this case, I'm going to use a pattern that I like to call the mouse pattern to know what to ignore. So let's, as always, I like to open up YED and do my my exploratory notes there. And I'm going to start with a very basic abstract state. Okay. The first abstract state is message password not encrypted is shown. Okay. Now, recall that reachability graphs are merely representations of real states of the system under test. And because they are representations of real states, they are abstractions. Okay. Here we're just dealing with abstractions, so we're dealing with abstract states. Okay, we can't deal with, we could, but it would take too long, and there's a lot of irrelevant details that we don't care about. You know, probably the system time. There's you know, the sockets that are open that may be affecting the issue. But right now we're going to focus on the password not being encrypted, and then the other abstract state that we got. We're going to focus on the error message we got. Okay. So reachability graphs is all about, and abstract states too, is all about abstracting away or putting details that are relevant. All right. And instead of dealing with full-blown real states of the system that are hard to manage, hard to reason with, basically. Now, you'll recall from my previous video on reachability graphs that we know, due to the simple passage of time and the way the messages are shown in the dialog box, that first we know that the password non-encrypted message is shown, and then either no message or an error message is shown. All right, so we know that this state, this abstract state, reaches this abstract state. We also know that, I'm going to give it a name right there, that this abstract state reaches this abstract state. That was the first dialog box we got. All right, and then the second one is this guy. I'm going to give it the name too. Okay, so again, recalling on that previous video, you will remember that this represents the bicycle pattern. Basically, this means that there is an abstract state, there are properties or even abstract states that are missing between the first level and the second level. And that's certainly true. There are definitely some missing properties that we haven't seen which could explain the error. However, let's turn the reachability of the abstract states around and flip the arrows the other way. This can safely be done because abstract states that are reachable from one direction are usually, not always, but usually reachable in the reachable in the opposite direction. So here we will say that, so recall that this is a state with no error, even though there's a state with a fatal message right there. And then this is a state with an error and a state with a fatal right there. So we can actually also say that this state right here reaches this state right here, and this state right here reaches this state right here. All right, that's the reachability graph of these relevant abstract states that we're seeing via this dialog box. Okay. Now, how can we know that that's correct? Well, it's basically what we can observe, and we use the syllogistic inference rule, modus ponens, to reason and to verify that we can actually go both ways. So let's say, for example, I'm going to name this abstract state P, This is E, this is not E. And I'm going to say if P, then E. All right, if the password, the message password unencrypted is shown, then the error message is shown. Okay, and remember that reachability graphs are not causality graphs. We're merely reasoning about state reachability. That is all. And certainly we saw that that was the case, right? We saw that this error message was shown for one instance right here. All right, but we can't actually reason with this. For that, we will need to flip the states like that in the inference. Okay, so we know that this error message is shown. We know that the password unencrypted message is shown as well, and the inference is via modus ponens. Actually, it's the other way around. It is all right, there we go. That's the way. And the other one was also correct, but it just needed some tweaking. So via modus ponens, I know that this is the case. Okay, and the way you construct reachability graphs is from the conclusion to the premise. So from the conclusion to the premise. That's the arrow. And then the other way, before I decided to get confused, was, let's see, like this. Therefore E. If P, then E. We saw P, therefore E, which is true. And again, from conclusion to premise. From conclusion to premise. And we can do the same with the other one, basically because we already observed that that was the case. Just for fun, let's do that. If P not E, okay, and we observed also that such was the case. P not E. Therefore, from conclusion to premise, okay, and same thing with the other way, not E, then P. We definitely saw not E. Therefore P. Okay, from conclusion to premise. All right, so what I'm going to do now is remove the arrows for the bicycle pattern. And now that we know that we're safe to consider this this arrangement of abstract states because of modus ponens, because of also we've observed these states, let me organize the graph. And now you see something interesting. This reachability right here, I call it the mouse pattern. Basically, it's the little two ears and the face. The mouse pattern tells us that for these abstract states, this abstract state is irrelevant. So let me write that down. The mouse pattern deals with irrelevancy. Okay, so when you see this pattern, when you're using reachability graphs, you can be certain that either these two in the higher level, these two abstract states in the higher level are irrelevant to this abstract state in the lower level, or vice versa. This abstract state in the lower level is irrelevant to these two abstract states in the higher level. In this case, it's this guy, right? I mean, it's also the case that the error message is irrelevant to the password not encrypted. That's what the reachability graph is telling us. So with that information, we can go ahead and disregard the password not encrypted issue and not waste our time seeing if encrypting the password causes leads to the same error, because we have seen via the mouse pattern that the password is irrelevant to the error. Okay. Briefly, I just want to say the reason we can trust this is because there's it's closely related. Excuse me. It's closely related to the oracle problem, and there's a mathematical proof I'm going to show in a subsequent video of why when you get these abstract states right here, and basically, I'm just going to abstract away all the details and show you the pattern in its full glory, in the most general pattern. So basically, when you have two abstract states, one the negation of the other, reaching to the same abstract state, you know you can disregard this level or this level. Okay, if it is relevant for your testing, if this level P, for example, is relevant for your testing, then you can disregard this level. Okay, now if this level, if these abstract states are relevant to your testing, you can safely disregard this level in your testing and not waste time there. Alright, so that's all for today, and I'll see you in the next video. Happy testing!